Okay, so we have another very qualitative lesson again today, and probably relatively short one. So we have been learning Newton's laws of motion, and essentially making this connection between the motion and what causes motion. All right, and there is another quantity that jumps in. So with the first law, and I'll talk about that quantity being mass. I'll talk about in a minute. The first law helps us establish the fact that inertial frames do exist, and we saw that the Newton's laws are only valid in inertial frames of reference. They cannot be applied in non-inertial frames. And force is the agency which causes or which produces motion, and mass is the property that determines its resistance, a body's resistance to change in its state of motion. We'll talk about it in a minute. So let me just rewrite the second law's definition. So if you're applying an F net force, okay, this is F net force. In some texts, you may see it written as with a sigma before it. That means vector sum of all forces. Again, means the same thing, net force. If you apply an F net force on an object of mass m, it produces an acceleration a in that object. Okay, and the acceleration and the force are related to each other for a given body by that body's mass. Okay, mass is what scales the force and its response. Acceleration is its response. Okay, and one common mistake that people make is F is equal to ma. Although I have this equation, but this m times a is not a force, right? This is a response to a force. Okay, this is the force. This is the mechanical, the dynamic response, the change in the state of motion of the object. Okay, and this second law actually deceptively looks very simple. It's very complicated, and in fact, it's a dynamic equation. It's a differential equation in reality. If you allow me to write it like this, now we know that A is nothing but dV over dt. And dV over dt is dx over dt. So it's a double derivative with respect to time. All right, equals 1 over m times f. In reality, the real practical problems is when you solve this differential equation for a given force. We won't be doing this, okay? Or probably would be doing that in some way, because we would be doing it probably no, we won't be calling it a differential equation, and would have much more simpler forces here, but this provides a very nice connection. So before getting here, what we have been doing is, in the kinetics part of this lesson, going from a to v using the integral, right? Or using the integral, right? A to v to position vector r, and using the derivatives, we could start with r, we could go to v, we could go to a. But now we have found a relationship between the acceleration and the force. Okay, now this route is more what we would be taking. This one here would be finding force, would figure out what force is, then we do the acceleration from the force by this equation or by this equation. Okay, and then once we go to acceleration, we can go to velocity, and then we can go to position. But this equation tells you that you can directly go to position as well. But we won't be doing this in this course. This is probably beyond the level of difficulty that we are allowed in this course. But you could still get to the position vector through this route. Okay. I think we said this. You see that there is no negative sign here. So this is a vector. This is a vector. The acceleration is always in the direction of the force. The direction of the resultant acceleration is always in the direction of the force. But here we see another important quantity, mass, come in. Now we have an intuitive understanding of what mass is, right? So that it's a quantity of matter in an object, right? That's what mass is. But it's an intrinsic property. And can we measure it? How do we measure mass?
So
No.
weight divided by the gravitational acceleration.
Okay, good. Yes. And there is this comment here when we say F to A to V to R, do we mean that we can differentiate F to get A? No, you can't. So you see this, you can use this algebraic expression. Okay, the relationship between F and A is algebraic. You don't really need to do differentiation or integration. Just if you know forces and the mass, you can get the acceleration. You plug in the value of force, you plug in the value of mass, and you get acceleration. This relationship is algebraic. Okay. Yes. Once you get the acceleration, then the relationship of A to V is of integration, not differentiation. You have to integrate A to get to V, and then integrate V to get to R. And it makes sense. The double derivative appears here. So you have to do two integrations. This is more complicated form of the Newton's second law. So it provides the relationship between the position and the force, okay, through this second derivative, right? So how do we measure mass? So mass, it's very hard to measure mass because it's an intrinsic property of an object. And the only way we can do is we can pick up an object. We can pick up an object and we call this as a standard unit and then start comparing other masses in terms of these units. So this is when we compare masses with each other. But you can look at mass from another point of view, from something that is not intrinsic, something that is extrinsic, outside the body, okay? Something that we can measure. And I have to say it, acceleration is something that is very easy to measure. We can measure it in the lab. It's simply rate of change. So if you take the position of an object and you just take a clock and look at an object and then look at the position of the object at a later time and then make a position time graph or a position time function out of it, then you take the derivatives and it gives you velocity and it gives you acceleration. So acceleration is something that we can measure in the laboratory. So let's say, and I can rewrite the Newton's second law in this way as well. So mass is nothing but the ratio of force exerted on an object and the resultant acceleration. Okay? The magnitude of the force and the acceleration that it produces in a body, that ratio is always fixed for a given object. Okay, so any amount of force you apply to an object, it would produce more acceleration. The more force you apply, the more acceleration for a given object. This ratio stays the fixed. And this ratio between force and acceleration is what mass is in these terms. Okay. Now these are external quantities. We can measure them. So let me, for example, write. So let's say then you have another object. Let's call this M1. Let's say that you have M2. And the force exerted, any force, actually, I should not really write F1 here, or F1 is just to denote that we have the first case, but it could be any force that you apply on this object, whatever acceleration it produces in this object, the ratio of the two quantities of the ratio of the magnitudes of the two quantities would always give you the mass of the object. And this ratio would be different for different masses. Means the same force would produce different acceleration. The same force would produce different acceleration in two objects. So if I have M1 and I apply the same force F, it would produce acceleration A. And if I have another object M2 and I apply the same force, it would, now the mass is different, it would produce a different acceleration. From these two equations, I can write M2 A2 is equal to M1 A1, right? And I can write M2 equals A1 over A2 times M1. Okay. So this gives you that if you define a chunk of matter as the standard, so you take M1 to be your standard, okay, and then want to express all other masses in units of that chunk, the ratio of their acceleration for the same force would give you the new mass. So this you take M1 to be your unit mass, let's say, which is 1 kilogram in SI system of units. So then if you want to measure the mass of another object, you apply the same force on both of them, okay, and then you multiply the unit with the ratio of their accelerations, and it gives you the M2. So we can measure the M2, the masses of objects in a laboratory, okay, and express masses as a ratio of their accelerations. Like this, M2 over M1 is equal to, right, A1 or A2. It's an inverse ratio between accelerations. So mass really is, you can do several experiments in the laboratory, and also it's part of our common experience that mass is, and this is very important, mass resists change in its state of motion. And the change in state of motion is not very high speed or going or being at rest. It is the transition between a position of rest to a position of motion. So it really resists the change in state of its motion, which means if an object is traveling with a constant speed and you want to increase its speed, whatever mass that object has would resist that transition, would resist that change. All right. And if you have an object at rest and you want to accelerate it, it is the mass that resists that change in the state of motion. So if an object is moving with a constant velocity and you want to bring it to rest, it is the mass which resists this transition. But once you have achieved a constant speed, the mass plays no role. So once an object is moving at a constant speed, the mass has no role in it. So now if you have two objects moving at the same speed and one has larger mass and the other has smaller mass, and if you want to bring them to rest, the one with the larger mass would be difficult to bring it to rest. Okay.
सर मैंने आपसे एक चीज़ पूछनी थी। अब जैसे ये वाला जो आपने रिलेशन बताया है, अगर जैसे फॉर एग्जांपल दो ऑब्जेक्ट्स हैं और उन पे सेम एक्सेलरेशन प्रोड्यूस हो रही है, तो ये फॉर्मूला ये इम्प्लाई करता है कि दोनों का मास भी इक्वल होगा। और ये कुछ केसेस में ट्रू मेरे ख्याल से नहीं होता। जैसे फॉर एग्जांपल इफ यू हैव टू ऑब्जेक्ट्स ऑन द सरफेस ऑफ अर्थ, उन दोनों पे ग्रेविटेशनल एक्सेलरेशन सेम है, लेकिन इट्स नॉट नेसेसरी कि दोनों का सेम मास होगा।
Sorry, I don't get your point. I'm saying for the same force, this formula is true if the force on object 1 is equal to force on the object 2. Okay, this is the condition. Does it make sense now, or it still doesn't?
Yes, it does. I thought they were different forces, as one was F1 and the other was F, तो मैंने assume किया था
No. When I stated this, I said the same force. Okay, so this is
Right.
always the case.
Sorry.
Now, from the common experience, as I'm saying, that the acceleration is inversely proportional to the mass of the object for a given force, of course. And the force is directly, acceleration is directly proportional to the force, okay, for a given object. All right. So if you combine these two equations, you should get, as we are used to, A equals F over M. But do we get a constant of proportionality as well or no? What about C? Do we get it or we don't?
So C would be 1, I think so.
Why 1?
Because in the equation it is F is equals to ma, so then the constant would be 1.
Well, forget about the equation. Let's say that we have these two empirical observations. Okay. Let's say that Newton is at this stage in his experiments. Okay. So his experiments is showing that acceleration is inversely proportional to the mass and is directly proportional to the force. Okay. Now he has to write an equation out of these two proportionalities. Okay. So what do you think? Would he directly write A is equal to F over M, or he would write A is equal to C times F over M?
There should be a constant. C times.
Sir, I'm not sure if this is correct. By the way, am I audible?
Yes, yes, go ahead.
I'm not sure if this is correct, but for the first equation where A is directly proportional to 1 upon M, he could say that the constant of proportionality would be a constant force. And then that would make it true. I mean, I think this would be a jump though. I'm not sure. And he could say the opposite for the second equation.
Yeah. So there really should be a constant, and there isn't one. And it wouldn't hurt if you plug in a constant. What difference would it make if I just set C equals to T? Have the constant and have its value 1. Sorry, 2. What difference would that make?
So obviously वो value को affect करेगा, गलत value आ सकती है.
कोई फर्क नहीं पड़ेगा. They would, because we haven't really defined the units of force. Okay? The units of force would change, nothing else. The physics would remain the same. All right. So let's see. So what we have usually is this: A is equal to F over M. Okay. Now we know acceleration. We have been measuring it. We have been dealing with it. It's, what is acceleration? Meters per second, right? And we also have just defined the unit of mass. So it's kilogram, right? So if I write ma equals F and introduce the units, okay, then I would be able to deduce the units of force. So, and then also get the definition from here. So if I have 1 kilogram object that accelerates by 1 meter per second square, then what I would get is, I could say any number here. I could say this would be 2 newtons. And then my constant of proportionality would be 2. So this is where this constant of proportionality goes to 1. This is where it comes from. So we choose the units in such a way that C turns out to be 1. Okay. And we define.
सर आप प्लीज दोबारा बता सकते हैं जो end वाला आपने बताया बिल्कुल.
So this is just a definition. Okay. This is the definition of 1 Newton. Okay. So
Right.
we have to define a unit for force. Okay. It's a new quantity we are introducing, and we haven't really arrived at the units. But these units cannot be independent of the units on this side. It's related to these two physical quantities, mass and acceleration. We know their units, right? Mass is kilograms, and acceleration is meter per second square.
Right.
Now it would be ideal to define the units in these terms, okay, and not have a constant of proportionality have non-unitary value. So what I mean is this: I'm saying when a 1 kilogram object accelerates by 1 meter per second square, I want to call it 1 unit. This looks nice. That would make C equals 1. any other definition of the unit, any other definition of the unit of force would make C non-1. Okay, then C would not be equal to 1 if you had any other units. It's a fundamental equation, not in this sense, but we also set the unit of force. And you will see and all other expressions of the force wherever in physics. For example, the gravitational force, the Hooke's law's force, the spring force, or any other fundamental force, you will see that the constant of proportionality is not 1 there. Okay? It's because this is the equation which used to define the unit of force, and we take C equals to 1 because we said this is what we want to be 1 unit of force. When this much acceleration for this much mass is happening, we want to call it 1 unit of force. And now we call it a Newton.
सर बस इसका मतलब यही है कि अगर साइंटिस्ट चाहते तो 1 न्यूटन की जगह इसको 2 न्यूटन भी कर सकते थे डिफाइन।
जी बिल्कुल, फिर यहाँ कांस्टेंट ऑफ पर्सनैलिटी आ जाता।
ठीक है सर।
ठीक है, so the choice is arbitrary. The choice of units is arbitrary, okay? But once you have agreed on Newton, now all the equations when we write for the equation, they have constant of proportionality. You could also think of this, for example, you could take the force of gravity and you see that there is a G there, right? Capital G, the gravitational constant, right? So, or you could take Hooke's law. Now K is not 1 here, it's a constant of proportionality here. So if you define the units of force from this equation, taking K equals 1, if you started here and define units using this equation, okay, then C would not be 1, would not be 2, but we would have to work it out. Then you would have to work out what C would be. Okay. So this is the choice that we make about units using Newton's second law, and then all other equations have a constant of proportionality. It does not. Or it does. It's just this value is 1. So now we have the unit of force. What is 1 Newton? 1 Newton is 1 kilogram meter per second square. It's written as 1 N. Oh, sorry, is written N in the short. Any other questions about the Newton's second law? Because I'm starting the Newton's third law now. What is Newton's third law? Anyone?
Every force has
an equal and opposite reaction.
One person or better write it in chat. जी Amina Jamal जी, go ahead, आप बताएं.
I said every action has an equal and opposite reaction.
Every action has an equal and opposite reaction. Okay, so every action has more people. Every action equal and opposite reaction. Okay, what does that mean? So for example, this chalk is being pulled down by Earth, right? Right? The Earth is exerting a force on it, right? And if action and action are equal and opposite in reaction, then Earth is exerting the same amount of force on the, the chalk is exerting the same amount of force on Earth, right? Right?
Yes, sir.
Yes.
Then if I keep it here, would I be able to pull the Earth up?
So the mass of the Earth इतना ज़्यादा है कि the acceleration जो बन जाती है वो irrelevant होती है.
ठीक है, अच्छी, good, very okay. So let's look at another example. Do you see this duster here? This duster here, probably. So if I push on it, so I'm acting on it. I'm exerting a force on it. So there is action, right?
Yes.
And there is a reaction.
Yes.
If action and reaction forces are equal and opposite in direction, then why is the duster moving?
So there is a limit to the reaction जो आपको basically पीछे आ रही है due to friction. आपकी जो force है उसको exceed कर रही है, therefore एक आगे net force बन रही है.
Hmm. So there is a limit to reaction, right?
Yes.
Yes. Okay. An external force provided by you. Well, that's action. External force is my action. So I'm exerting a force, and the duster is exerting a force back on me. The duster is moving.
Actually, नहीं sir. Is horizontal and vertical components से balance नहीं हो जाएंगे in the end? या maybe नहीं. मुझे नहीं पता sir मैं क्या बोल रहा हूँ. छोड़.
All right. So this is a problem that the third law is actually it's this definition is not correct what you are used to. Okay. And now pay attention, please. Okay. Third law. The third law is the force if an object A exerts a force on B. Okay. The object B exerts always an equal and opposite force on A. When we are looking at the motion of object B, how many forces are acting on object B? Only this force, one force. एक force है, दो नहीं है, एक force है. This is the source of confusion.
सर वो नीचे से नहीं आ रही है फोर्स?
जी?
ये नीचे वाला एरो.
नहीं, this is just to point it out. Okay, sorry. So when we are considering the motion of object B, okay, there is only one force acting on this object. And whatever is reaction is, we don't worry about it when we look at the dynamics of an object. Okay? We absolutely look at the force that is acting on B. We don't look at the force acting on A. So now let's rationalize it. When I'm exerting a force on this duster, the duster's motion responds to the force that I am exerting on the duster. It has really nothing to do with the force duster is exerting on me. Okay, although it's exerting on me exactly the same force, the same amount of force in opposite direction. But then when I have to discuss my motion, I will talk about the force that duster is exerting on me. Okay, so this first confusion, you should never have this confusion, because sometimes you have this notion that action and reaction are opposite in direction, equal in magnitude, so they cancel each other. They never cancel, because they are never on the same body. Action is on the duster. The action is by me on the duster, and the reaction is by the duster on me. So when we are talking about the duster, all we have to focus about is the force that is acting on that duster and its response being produced in the duster.
सर हम लोग ये कह सकते हैं कि जैसे जब आप एक फॉरवर्ड फोर्स एग्जर्ट कर रहे हैं डस्टर पे, तो आप फोर्स डस्टर पे एग्जर्ट कर रहे हैं, लेकिन उसकी जो फ्रिक्शनल फोर्स है इट्स बिटवीन द डस्टर एंड द सरफेस, नॉट यू एंड द डस्टर. तो इस वजह से वो आगे जा रहा है. कैन वी से दैट?
Can you say again, please?
सर मैं कह रही हूँ कि जब आप एक फोर्स एक्सर्ट करते हैं डस्टर पे एंड इट मूव्स फॉरवर्ड, तो आप फोर्स एक्सर्ट करें डस्टर पे, लेकिन जो फ्रिक्शन है वो डस्टर और सरफेस के दरमियान है, वो आपके और डस्टर के दरमियान नहीं है. तो इस वजह से वो शायद आगे जा रहा है. कैन वी से दैट? क्योंकि डिफरेंट सोर्सेज पे वो
नहीं, अभी don't bring in friction. Let's imagine that we are in a frictionless universe. There is no friction. Okay, there is no friction. Duster has certain mass, and I have a certain mass. Okay, now I am pushing a force F on the duster. Okay, this direction of the force on duster is in this direction. This is its magnitude, this is its direction, and this is the mass of the duster. In a frictionless universe, it would produce an acceleration that is given by F over m. It would produce an acceleration, this much acceleration in the duster. Okay? The force that I'm exerting. Now, that's all that you need to worry. Although the duster is exerting a force back on me, but that force does not figure in any of the motion of the duster. This is very important. The forces, the action, reaction never cancel each other. It's just that all we have to worry about is this, the force that is acting on the duster would produce an acceleration.
Right.
Okay. Now, if you want to talk about why am I not moving, let's say in a frictionless universe, why am I not moving backwards? In a frictionless universe, I would move backwards. Okay. My acceleration would be due to the same force again, F over M. Now the response, the force is always equal and opposite, but the response does not have to. Okay. The acceleration produced by the force, the same force F. First of all, this would be in two different directions. This acceleration would be in this direction. And this acceleration would be in this direction. We are pushing each other. I'm pushing the duster this way. The duster is pushing me in this way. Both of us, if we live in a frictionless universe, both of us would move. But if the disparity between my mass and the duster is huge, I would move by a very small amount. Okay. Now the same force would produce a much more noticeable acceleration in the duster than it would produce in me, because it's the force is divided by mass, and my mass is huge, infinite compared to the duster. It's a very light object.
Sir.
Yes.
सर तो बेसिकली फोर्सेस सेम होती हैं लेकिन एक्सेलरेशन डिफरेंट होती है जब भी ऑब्जेक्ट एक मूव करता है और एक मूव नहीं करता.
हाँ जी, फोर्स दो चीजें आप याद रखेंगे, दो चीजें हैं ना कि ये फोर्सेस सेम है लेकिन इनका मैग्नीट्यूड सेम है, डायरेक्शन इनकी अपोजिट है, एंड देयर इज अ थर्ड मोर इंपॉर्टेंट क्रिटिकल डिफरेंस, दे आर एक्टिंग ऑन टू डिफरेंट बॉडीज. The force of action is being exerted by the person on the object M. The force of reaction is being exerted by the object on the person. That is why they never cancel each other, and that is why we see the duster is moving. And now if you bring in friction, then this force, I have a much larger, not just much larger mass, but I also have a much larger friction, and there would be nearly no acceleration in me. Okay, it was going to be very small acceleration anyway, and then if you allow in friction, then this force would not be able to produce any acceleration in me. But on this case, if I exert very small force, there is the duster's resistance is also resisting. But once I keep increasing action, the action force, of course, the reaction force is going up, but I get over the friction limit of the duster sooner than my own friction limit that is coming from the reaction force, and then that is why the duster starts moving, but it takes a while before it starts moving. Yes, this somebody wrote it. Excellent. The forces would only cancel if both forces act on the same body. Yes, whenever we take vector sum of forces, it only makes sense when we are taking all the forces acting on the same object.
सर एक क्वेश्चन है.
Yes.
जब हम ऑब्जेक्ट ए की एक्सेलरेशन लेंगे रिलेटिव टू बी, तो फिर दोनों की एक्सेलरेशन का सम हो जाएगा वो?
वो तो फिर आपका ऑब्जर्वेशन पॉइंट है ना, वी आर नॉट टॉकिंग अबाउट कि एक्सेलरेशन सम क्यों हो जाएगा. यस, आई मीन if you're looking from outside and both objects are accelerating away from each other, it's very hard to say which one is accelerating with respect to what when you just look at the two of them, but that's a different question.
ठीक है सर.
ठीक है ना. So then what is Newton's third law now? That if object A exerts a force on object B, or if one body exerts a force on another body, that the second body exerts the same force in magnitude but opposite direction on the first body. So the two forces are being exerted on two different bodies. They cannot be added up. They cannot be cancelled. There is another very important aspect of Newton's third law. And that is, let's say we have an object A. it has a mass m, and then we have another object. Actually, the same object, the copy of the same object, okay, twice. Now, if we say that A is exerting a force on the other A, okay, we could just call it B, but the same mass, let's say. Okay. Okay. If Newton's law, if Newton did not state it, it was genius. If Newton didn't state it, we would run into this problem. You see, these two objects are identical. What makes A so special that it exerts a force on B, but then B doesn't exert a force on A? I mean, this choice is arbitrary. Do you see that? See this?
Yes, sir.
So this is the only logical way for two objects to interact ever. Whenever two objects interact, there is symmetry in the relationship. There is symmetry in the interaction. There is no reason. It's impossible to justify that one object interacts with B. It is like I shake hand with somebody without them shaking hand back with me. So the interaction, it is two-way and it is symmetric. That is what it means. Otherwise, we would run into problem. Otherwise, we would say an electron exerts force on a proton or a positive charge, but then the positive charge does not exert any force on the electron. Can you conceive that? No. That is why this two-way relationship between forces, this is the symmetry in the interaction between two objects. The two-body interaction is symmetric. It goes both ways. And then the question of if it is not clear to everyone is that if the same force is acting, and it is actually the same force that Earth exerts on a chalk. Okay, the one I have it in my hand. Okay, and then the chalk exerts the same force on Earth. Okay. There is no friction involved here, and you see that the mass of the Earth is in the denominator. That is why mass Earth never accelerates. It's always the chalk that looks accelerating. It is not because the action reaction cancel. It is also not that there is some threshold on the force. So any questions about the third law before I move on? And one last time I'd say, the action reaction forces are equal only in magnitude. They are opposite in direction, and their responses never have to be equal. I mean, they can be equal if they actually can never be equal, because the acceleration they would produce, even it was two identical masses pushing on each other or pulling on each other, the reaction force, the reaction would be different in the sense that it would produce motion in the opposite direction. Okay.
I had a question.
Yes.
I wanted to ask if the F that is being exerted on any object is given by F equals to ma of the source object, right? Of the object that's the force.
Sorry, come again, please.
So for example, if there is a bus that's that's accelerating at some value and has some mass capital M, so the force that it will exert on something that it hits will be F equals to ma, right?
Sorry, can you speak slowly, because there is noise in the.
Okay. I wanted to ask. I was asking, for example, if there's some object of mass M and that's accelerating at A, the force it will exert on
So you're saying that this is an object which has mass m, okay,
accelerating at a in some direction,
accelerating at a in some direction, yes.
and it hits an object. The force it would exert on that object would be F equals to ma, right?
That this exerts. Oh yes, classic question. Very good question. Thank you for asking this. And the answer is no. And I won't go into the explanation of this right now, but when we go to conservation of
Okay.
momentum, we will talk about it. Okay, there is no, the force exerted on when an object hits another object, the force exerted on that object is never F is equal to ma. Okay, it's a lot of things, but never
Okay,
F is equal to ma. Okay, and that is why actually you have asked and answer a question. A lot of people, start a student ask, why do we you have to use a conservation of momentum and don't use the Newton's law? The Newton's law fails because the point when you come into contact and then you recede, the force becomes time dependent. If you plot a time, the force peaks at some point to whatever value, and then it goes down, and it's very difficult to deal with a time dependent force. The force that is being exerted by this object on this object, okay? That is why we have
Okay, sir.
laws of conservation of momentum. They're much easier to apply to situations like this, particularly collisions. Okay, so the last bit about today's lesson is so we talked about the non-contact forces and the contact forces, and then we also discussed that in essence, all the forces emerge from the fundamental forces, which are three: the force of gravity, the electromagnetic force, and of course the other two forces, the electric weak force and the nuclear strong force. We would never have to deal with them, okay, in this course. They're far too at a different scale than we are dealing with in this lesson. So then we would be dealing with contact forces, the pulling, the pushing on a string or stretching a spring, for example. So those all forces fundamentally come from the electromagnetic force or the electric force. And they one of the most important force, because we have been always implicitly using it, is the gravitational force. So its mathematical formulation is that if you have an object mass m1, let's call it object A with mass A, and if you have an object B and mass B, the force, the gravitational force between the two of them would be G, a constant, the gravitational constant, mass of object A, mass of object B over r squared, where r being the distance between the two objects. All right. And if I want to use a vector notation, because this force is a vector, and so let me write it another way so that it makes more sense. I like this notation. So here I'm talking about force exerted by B on A. What? Force exerted on B, force exerted by B on A would be given by this expression. And if you want to write its direction, what would be the direction of the force?
सर वो दोनों
इसका
masses
तो
पे नहीं depend
A
करता.
to B हो जाएगी सर.
Direction does not depend on the masses. It would always point towards B, towards the center of B, okay? So if I want to write it in the vector form, I could just define a vector AB, a unit vector. So it would be along this unit vector, a unit vector going from A to B. So this would be the force. Force being exerted by B on A. And then if you want to write the force being exerted by A on B, it would be same in magnitude, but opposite in direction. MA MB over R squared E AB, the same vector, okay? Otherwise, you don't need a minus sign. Okay? So once you set the frame of reference, one of the force comes down with the negative sign, because this is to indicate the force is pointing towards A. So the first expression tells us the magnitude of force is given by these constants or these quantities here. So G, the gravitational constant, mass of the object A, mass of the object B, and the separation between the two objects. Okay, and it's pointing from, the force is being exerted by B. It's a pulling force. B is pulling A towards its center. And then in the second case, A is pulling B towards its center A. Okay, they are only equal in magnitude and they're opposite in direction. So, and in a way, both objects are pulling each other towards each one towards themselves. Okay, each other towards themselves. So this was, of course, Newton realized it, and that what he realized was very interesting. He realized that this was the same force that was responsible for the planets going around, let's say the moon going around the earth, and the same force was responsible for the free fall of objects, let's say an apple on earth. So Newton realized that it was the same force. Okay, and the second thing he realized was he used this to work out the orbits of the planets, and he figured out that they were ellipses. They had been suggested before, but Newton used this quantitative relationship. So he not only said, in a way, it's an extension of the third law, okay? The two objects interacting, they always exert force on each other, all right? So it's consistent with the third law. But he not only said that they interact with each other, two objects having a mass, not they interact with each other, but they interact with exactly this much amount of interaction, this much amount of force. And then when he realized that it was the same force which was responsible for the fall of an apple on Earth and making the moon go around Earth, he used this and figured out the ellipses he figured out the orbits of the planets, that they were ellipses. And he also figured out that the fall rate was consistent, that the fall rate of objects on the surface of Earth is independent of mass. And we'll probably see it in a minute if I can figure that out, okay? And this, of course, another huge jump was, and it was quite counterintuitive at that time, that this was a non-contact force. It was not, Newton didn't talk about it, and since it works so well on so many of the known phenomena, nobody really questioned it, that how is it possible that Earth is able to exert force on moon so far away? Okay, so this is a non-contact force, or in other words, action at a distance. But then we will see that so many times, why don't we consider the gravitational force between a lot of objects that we would be dealing with, for example, moon and Earth, or these small objects like a chalk and Earth. But why don't we consider the force of attraction between, for example, myself and the laptop, or a chair, or the force of attraction between two chairs? What do you think about that? And the reason is because it was, yes?
Sir, there is one present, like on the Earth, the friction that prevents them from moving is just too great for them to ever touch. I think if they were in deep space, eventually they would actually come together.
Yes, there is always a force of attraction whenever you have non-zero mass, any object. The problem is that this gravity is very, very weak force when you apply it to ordinary objects. And the reason is this gravitational constant is 6.61 to 10 minus 11 meters cube kilogram second per kilogram per second square. Okay, so this is the gravitational constant. It's very small. So look at here. If you have a small mass, let's say 1 kilogram, okay, and even if they are very small distance apart, the force would be what? More than what? 1 billionth, less than 1 billionth of a Newton, or even less than that, right? So that would be the force. The force is negligible, okay, for practical purposes. The force of attraction between. So the force only becomes significant when one of these two objects involved is just a product. When one of the two objects have a massive mass, like Earth or Moon or Sun. So now let's consider one last thing. So let's say this is Earth, and it has a certain radius R, call it RE, all right? And the R happens to be 6.4 to the power 9 meters, all right? And now we have an object here. We want to look at the force acting on this object due to Earth, okay? Some small distance. This distance can be several hundred meters. Let's call it H. Let's say that this is, we are not saying what this distance is, but let's say it's of the order of hundreds of meters. Okay. Now, what would be the force acting on this object of mass m? And let's say again, let's make it an ordinary object. Anything that we can send up in the air, from a football to a rocket. Okay. Mass in that range and the distance in hundreds of meters. And the force now, as you can see, if I use the formula, and I'm just talking about magnitude for now, okay, forget about the direction. So it would be G M, the mass of Earth, the mass of the object, and the distance now would become RE plus H squared. Does this make sense? I'm just writing the magnitude of the force. So the mass of Earth, mass of object, gravitational constant, and the distance. Distance is, of course, the radius of Earth and whatever height we are above the surface of Earth. Now you should divide both the numerator and denominator by RE. Or just take the RE common from here, okay? Doesn't really matter. RE squared 1 plus H over RE squared. Okay, see this? Now, what do you think about this number? A few hundred meters divided by about a billion meters. A few hundred meters divided by approximately a billion meters, or 6 billion meters, roughly 6 billion meters. So this is negligible. And we get back the approximate force on object would be the same as if the object was on the surface of Earth. Is this transparent?
सर अगर h ओवर r e बहुत छोटी वैल्यू होगी तो जब वो 1 से प्लस होकर स्क्वायर हो गया फिर r e स्क्वायर से मल्टीप्लाई होगी तो डिनोमिनेटर भी आपका बहुत ही छोटी वैल्यू नहीं बन जाएगा?
नहीं, फिर तो ये 1 के साथ मल्टीप्लाई होगा ना, तो ये
1 के साथ ऐड हो जाएगी एक बहुत छोटी वैल्यू एंड अच्छा से
तो उसका स्क्वायर भी अप्रोक्सीमेटली 1 के करीब ठीक है. So this is one thing. That's why we never worry about that acceleration is different or the force is different for our purposes in this course. But let me now write this force in a more suggestive way. Okay. Okay, what do you think about the quantity in parenthesis? Can you recognize it?
तो जी हो जाएगा.
Small g. So small g is
acceleration.
acceleration due to gravity. But remember, this expression of the acceleration due to gravity is only true very close to the surface of Earth, because we have ignored this quantity here. Eh? So when you go far away from the surface of Earth, then you won't be able to ignore this correction. Okay? This quantity here, and then g won't be the same. That's why we are saying g is only a constant when we are in the vicinity of Earth. So then we get mg, where g is gravitational acceleration.
सर हम कितना फार जा सकते हैं कि जी कांस्टेंट आ रहा है?
Yeah, there is no hard limit. You see, it's a very continuous limit.
ठीक है सर.
You can play with this ratio of these two numbers, and when this ratio starts becoming significant, it depends again on the sensitivity of the experiment. So if it's when this number starts becoming significant, but more importantly, when this number starts getting to a point, this ratio, where it starts making significant changes to f. Okay. So can you find out the ratio of this number which would make an error, which would give an error of 1 Newton? Can you do that as a homework assignment? So let's say that you ignore this contribution in one case, and then you introduce for this contribution for a given height. Take that height to whatever, okay, or keep it general, h, and express the error. So basically, I'm asking is, take the difference of this and this. Okay, and then set this difference to be equal to 1 Newton, and then find out h. For what h? Now give me a good idea for the next quiz. Thank you. So I just have one last thing to say. Actually, there are so many last things today. Sorry. And that is a free body diagram. How many of you are already familiar with a free body diagram? Say yes, no, if you're familiar with the free body diagram. Okay. Okay. So a free body diagram is, because we would be dealing with situations where we have an object, it could be a car or a bus or whatever, and there would be multiple forces. For example, the force of gravity, okay, the normal force acting upwards, the force of friction acting backwards, and maybe the engine or something, or somebody is pushing on this thing. A push, let's say if it is a cart. So now there's so many forces that you're pushing on a cart which has a certain weight which is weighing it down. Then there is a normal force because it's on a surface that's acting in the opposite direction. Then there is a force of friction which is resisting motion, and you're pushing. So 1, 2, 3, 4 forces working on it. So you would have to deal with multiple forces, okay? And the best approach to solve such problems is to replace your body, okay, with a point in space, or even just literally a point, okay, and draw all the forces. Choose a frame and draw all the forces as vectors properly with proper directions, okay. For example, like this, like this, like this. So this would be push, normal force, gravity, okay, and the force of friction. That's a free body diagram. So you just forget about the shape of the body, where the force is being exerted, reduce all the forces to one point, then make all the vectors, and then do a vector sum of the forces. And usually it's very convenient if you choose a coordinate system and then look at the x component of the force and y component of the force if you are in 2 dimension, z component if you are in 3 dimension. Okay. And then whatever forces, net force you get, then apply Newton's second law. So this is the concept of a free body diagram. And I think that's it. Thank you very much. Thank you.
सर मैंने आपसे पूछना था कि आप ऑब्जेक्ट को पॉइंट मास क्यों कंसिडर करते हैं, मतलब इससे